Systems of nonlinear equations and inequalities, two variables. Halley's Comet, Figure 1, orbits the Sun about once every 75 years. Its path can be considered to be a very elongated ellipse. Other comets follow similar paths in space. These orbital paths can be studied using systems of equations. These systems, however, are different from the ones we considered in the previous section because the equations are not linear. In this section, we will consider the intersection of a parabola and a line, a circle and a line, a circle and an ellipse. The method for solving systems of nonlinear equations is similar to those for linear equations. Solving a system of nonlinear equations using substitution. A system of nonlinear equations is a system of two or more equations and two or more variables containing at least one equation that is not linear. Recall that a linear equation can take the form of ax plus by plus c equals 0, and any equation that cannot be written in this form is nonlinear. The substitution method we use for linear systems is the same method we will use for nonlinear systems. We solve one equation for one variable and then substitute the result into the second equation to solve for another variable, and so on. There is, however, a variation in the possible outcomes. Intersection of a parabola and a line. There are three possible types of solutions for a system of nonlinear equations involving a parabola and a line. Possible types of solutions for points of intersection of a parabola and a line. Figure 2 illustrates possible solution sets for a system of equations involving a parabola and a line. No solution, the line will never intersect the parabola. One solution, the line is tangent to the parabola and intersects the parabola at exactly 1 point. And two solutions, the line crosses on the inside of the parabola and intersects the parabola at 2 points. How to? Given a system of equations containing a line and a parabola, find the solution. 1. Solve the linear equation for one of the variables. 2. Substitute the expression obtained in step 1 into the parabola equation. 3. Solve for the remaining variable. And 4. Check your solutions in both equations. Q&A. Could we have substituted values for y into the second equation to solve for x in example 1? Yes, but because x is squared in the second equation, this could give us extraneous solutions for x. For y equals 1, this gives us the same value as in the solution. For y equals 2, notice that negative 1 is an extraneous solution. Intersection of a circle and a line. Just as with the parabola and a line, there are three possible outcomes when solving a system of equations representing a circle and a line. Possible types of solutions for the points of intersection of a circle and a line. Figure 4 illustrates possible solution sets for a system of equations involving a circle and a line. No solution, the line does not intersect the circle. One solution, the line is tangent to the circle and intersects the circle at exactly 1 point. And two solutions, the line crosses the circle and intersects it at 2 points. How to? Given a system of equations containing a line and a circle, find the solution. 1. Solve the linear equation for one of the variables. 2. Substitute the expression obtained in step 1 into the equation for the circle. 3. Solve for the remaining variable. And 4. Check your solutions in both equations. Solving a system of nonlinear equations using elimination. We have seen that substitution is often the preferred method when a system of equations includes a linear equation and a nonlinear equation. However, when both equations in the system have like variables of the second degree, solving them using elimination by addition is often easier than substitution. Generally, elimination is a far simpler method when the system involves only two equations and two variables, a 2x2 system, rather than a 3x3 system, as there are fewer steps. As an example, we will investigate the possible types of solutions when solving a system of equations representing a circle and an ellipse. Possible types of solutions for the points of intersection of a circle and an ellipse. Figure 6 illustrates possible solution sets for a system of equations involving a circle and an ellipse. No solution, the circle and the ellipse do not intersect. One shape is inside the other, or the circle and the ellipse are a distance away from the other. One solution, the circle and ellipse are tangent to each other and intersect at exactly 1 point. Two solutions, the circle and the ellipse intersect at 2 points. 3 solutions, the circle and the ellipse intersect at 3 points, and 4 solutions. The circle and the ellipse intersect at 4 points. Graphing a nonlinear inequality. All of the equations in the systems that we have encountered so far have involved equalities, but we may also encounter systems that involved inequalities. We have already learned to graph linear inequalities by graphing the corresponding equation and then shading the region represented by the inequality system symbol. Now we will follow similar steps to graph a nonlinear inequality so that we can learn to solve systems of nonlinear inequalities. A nonlinear inequality is an inequality containing a nonlinear expression. Graphing a nonlinear inequality is much like graphing a linear inequality, and recall that when the inequality is greater than y greater than a or less than y less than a, the graph is drawn with a dashed line. When the inequality is greater than or equal to y greater than or equal to a, or less than or equal to y less than or equal to a, the graph is drawn with a solid line. The graphs will create regions in the plane, and we will test each region for a solution. If one point in the region works, the whole region works, and that is the region we shade. See Figure 8. How to. Given an inequality bounded by a parabola, sketch a graph. 1. Graph the parabola as if it were an equation. This is the boundary for the region that is the solution set. 2. If the boundary is included in the region, the operator is less than or equal to or greater than or equal to. The parabola is graphed as a solid line. 3. If the boundary is not included in the region, the operator is less than or greater than. The parabola is graphed as a dashed line. And 4. Test a point in one of the regions to determine whether it satisfies the inequality statement. If the statement is true, the solution set is the region, including the point. If the statement is false, the solution set is the region on the other side of the boundary line. And 5, shade the region representing the solution set. Graphing a system of nonlinear inequalities. Now that we have learned to graph nonlinear inequalities, we can learn how to graph systems of nonlinear inequalities. A system of nonlinear inequalities is a system of 2 or more inequalities and 2 or more variables containing at least one equality that is not linear. Graphing a system of nonlinear inequalities is similar to graphing a system of linear inequalities. The difference is that our graph may result in more shaded regions that represent a solution than we find in a system of linear inequalities. The solution to a nonlinear system of inequalities is the region of the graph where the shaded regions of the graph of each inequality overlap or where the regions intersect, called the feasible region. How to. Given a system of nonlinear inequalities, sketch a graph. 1. Find the intersection points by solving the corresponding system of nonlinear equations. 2. Graph the nonlinear equations. And 3. Find the shaded regions of each inequality. 4. Identify the feasible region as the intersection of the shaded regions of each inequality or the set of points common to each inequality. Access these online resources for additional instruction and practice with nonlinear equations. Solve a system of nonlinear equations using substitution. Solve a system of nonlinear equations using elimination. OpenStacksCollege.org. Partial fractions. Earlier in this chapter, we studied systems of 2 equations and 2 variables. Systems of 3 equations and 3 variables in nonlinear systems. Here we introduce another way that systems of equations can be utilized, the decomposition of rational expressions. Fractions can be complicated. Adding a variable in the denominator makes them even more so. The method studied in this section will help simplify the concept of a rational expression. Decomposing P of x over Q of x, where Q of x has only non-repeated linear factors. Recall that algebra regarding adding and subtracting rational expressions. These operations depend on finding a common denominator so that we can write the sum or difference as a single simplified rational expression. In this section, we will look at partial fraction decomposition, which is the undoing of the procedure to add or subtract rational expressions. In other words, it is a return from the single simplified rational expression to the original expressions called the partial functions. For example, suppose we add the following fractions: 2 over x minus 3 plus negative 1 over x plus 2. We would need to first find a common denominator, x plus 2 multiplied by x minus 3. Next, we would write each expression with this common denominator and find the sum of the terms. Partial fraction decomposition is the reverse of this procedure. We would start with the solution and decompose it as the sum of two fractions. X plus 7 over x squared minus x minus 6 simplified sum equals 2 over x minus 3 plus negative 1 over x plus 2. Partial fraction decomposition. We will investigate rational expressions with linear factors and quadratic factors in the denominators, where the degree of the numerator is less than the degree of the denominator. Regardless of the type of expression we are decomposing, the first and most important thing to do is factor the denominator. When the denominator of the simplified expression contains distinct linear factors, it is likely that each of the original rational expressions, which were added or subtracted, had one of the linear factors as the denominator. In other words, using the example above, the factors of x squared minus x minus 6 are x minus 3 multiplied by x plus 2, and the denominators of the decomposed rational expression. So we will rewrite the simplified form as the sum of individual fractions and use a variable for each numerator. Then we will solve for each numerator using one of the several methods available for partial fraction decomposition. Partial fraction decomposition of p of x over q of x, where q of x has non-repeated linear factors. The partial fraction decomposition of p of x over q of x, when q of x has non-repeated linear factors and the degree of p of x is less than the degree of q of x. How to? Given a rational expression with distinct linear factors in the denominator, decompose it. 1. Use a variable for the original numerators, usually a, b, or c, depending on the number of factors, placing each variable over a single factor. For the purpose of this definition, we use a sub n for each numerator. 2. Multiply both sides of the equation by the common denominator to eliminate fractions. 3. Expand the right side of the equation and collect like terms. And 4, set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Decomposing p of x over q of x, where q of x has repeated linear factors. Some fractions we may come across are special cases that we can decompose into partial fractions and with repeated linear factors. We must remember that we account for repeated factors by writing each factor in increasing powers. Partial fraction decomposition of p of x over q of x when q of x has repeated linear factors. The partial fraction decomposition of p of x over q of x when q of x has repeated linear factor occurring n times and the degree of p of x is less than the degree of q of x. Write the denominator powers in increasing order. How to? Given a rational expression with repeated linear factors, decompose it. 1. Use a variable like a, b, or c for the numerators and account for increasing powers of the denominators. 2. Multiply both sides of the equation by the common denominator to eliminate fractions. 3. Expand the right side of the equation and collect like terms. 4. Set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Decomposing p of x over q of x, where q of x has a non-repeated and reducible quadratic factor. So far, we have performed partial fraction and decomposition with expressions that have had linear factors in the denominator, and we applied numerators, a, b, or c representing constants. Now we will look at an example where one of the factors in the denominator is a quadratic expression that does not factor. This is referred to as an irreducible quadratic factor. In cases like this, we use a linear numerator such as ax plus b, bx plus c, etc. Decomposition of P of x over Q of x when Q of x has a non-repeated irreducible quadratic factor. The partial fraction decomposition of P of x over Q of x such that Q of x has a non-repeated irreducible quadratic factor and the degree of P of x is less than the degree of Q of x. The decomposition may contain more rational expressions if there are linear factors, and each linear factor will have a different constant numerator, a, b, c, and so on. How to? Given a rational expression where the factors of the denominator are distinct, irreducible quadratic factors decompose it. 1. Use variables such as a, b, or c for the constant numerators over linear factors, and linear expressions such as a sub 1, x plus b sub 1, a sub 2x plus b sub 2, etc. for the numerators of each quadratic factor in the denominator. 2. Multiply both sides of the equation by the common denominator to eliminate fractions. 3. Expand the right side of the equation and collect like terms. And 4. Set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Decomposing P of x over Q of x, where Q of x has a repeated irreducible quadratic factor. Now that we can decompose a simplified rational expression with an irreducible quadratic factor, we will learn how to do partial fraction decomposition when the simplified rational expression has repeated irreducible quadratic factors. The decomposition will consist of partial fractions with linear numerators over each irreducible quadratic factor, represented in increasing powers. Decomposition of P of x over Q of x when Q of x has a repeated irreducible quadratic factor. The partial fraction decomposition of P of x over Q of x when Q of x has a repeated irreducible quadratic factor and the degree of P of x is less than the degree of Q of x. Write the denominators in increasing powers. Systems of nonlinear equations and inequalities, two variables. Haley's comment